We call this the anchorage zone design. In some cases, it's called end block. And we're going to have here 3 slide set on it. So this is going to be slide set number 1-1. So this is going to be the first one. Then I'm going to have 9-2 and then 9-3. I posted already 9.1 and 9.2. 9.3 is going to be coming very soon. So what happened, I split this anchorage zone design on 3 slide sets, if you like. When it comes to the design of pre-tension end block or anchorage zone, it's going to be different from the design of post-tension end block. Just 2 different philosophies, 2 different type of force transfer from the cable itself or from the strand to the concrete beam itself. So first, let's talk about what happened at the end block, or this anchorage zone, if you like to call it this way, and what type of stresses we are talking about. So just speaking, here is a pre-stressed beam. It doesn't matter whether it's going to be a pre-tension or post-tension, but we have the cables, they're going to be draped, and then at a certain point, we're going to provide the anchorage right here. At this anchorage location, you're going to have some forces coming this way. So the force here is going to be compression on the concrete, while it's going to be tension on the strands themselves. So the strands themselves is going to be exposed to tension, and this tension, once you put this anchor, they're going to be providing compression on the end block of the beam. Now, this high compressive stresses is going to be causing some trouble here, because all of a sudden you're going to put all the stresses is going to be at the end. This is where you transfer the force. Whether you have pre-tension or post-tension, transfer of the force is going to happen in this location. I'm going to say roughly in this area. And this is the reason that you see here this piece to be solid, right? See, this is solid here. And right here, if you cut the section, it's going to look like an I-beam. So in here is going to look like an I section, and here's going to be a rectangular section. So why do we need this rectangular section? Because we have high compressive stresses at this place, and we need to provide some reinforcement to prevent cracks from happening at this location. So if you look here at what happened at just one bearing plate, if you like, you call this a bearing plate or the anchorage plate. You're going to put one big force, right? And most likely you're going to have a few strands, but at the end, we're going to put the resultant as one big force. And then you think here that this force is not transferred at one point, unless you have post-tension. So if I have post-tension and there is no bond between the concrete and the strands, all the force is getting transferred at this point. But if you have pre-tension or the strands are grouted, it's going to take some time here before you transfer the entire force from the strand to the concrete. So if you put the force right here, the pre-stressive force right here as compression on the concrete, you're gonna give it some distance here before you're gonna have this uniform distribution of stresses. It's not gonna happen right away, because think about it this way. If I'm gonna put here a point load right at this location, just imagine that you put a point load right here. Do you think you're gonna have any stresses at this point? Any compressive stresses? Right at this point. Let me put it right here. If you put an axial force right concentrated here only, actually this area here, you're not gonna see any compression at all in this location. This distribution is okay right here at this section if you would put a big plate. Big and rigid plate, you put it right here, a very stiff plate. You start to put the pressure. So in this case, you're going to say the stress distribution right below the plate, right behind it, is going to look like this. But if the stress or the force is going to be concentrated at a certain location here only, it's going to take some time before the stresses here is going to get uniform, like in this shape. And this is what we hear, this is what we call the stress trajectories. And this is going to show here how the stress is going to be moving from one point all the way to the end point. So the stress is going to be uniform after a given section here. So right here at this section, you see what happened to the stresses, compressive stresses. It's shown like solid lines. So in this location here, you have no axial compressive stresses at all. Same thing here, but after a certain distance, you're going to have this uniform distribution of stresses along the entire depth of the beam. Meaning, if I'm going to be taking a section here, stress distribution is going to be only in this location. And here, no stresses at all, and here, no stresses. And you may have some tension in this location. You may have some tension in this location. But all the compressive stresses going to be only in this location. If you change the section, if I decide here to take a section right here, the stress is going to be concentrated only on this location here. Let me draw this box. So in order for you to bring the stresses from being concentrated on one little section of the beam to the entire beam depth, it's going to take some distance. And this distance usually ranges from 1 times the depth to 2 times the depth. Most likely it's going to be equal to 2d. So if the distance from here to here, if you like to call it h or d, so for now let me call it h. This horizontal distance is roughly, if you like to do some quick analysis, you say this is going to be from h to 2 times h. And most likely it's going to be equal to 2 times h. People would prefer to make it like 2 times h. And the question is, what happened here? I mean, when you look here at the stress is going this way, what's going to be the resultant of having the stress coming this way? So here's going to be uniform. But here, if I put, let's say, I'm going to divide here this area into small areas, right? So I'm going to make it like this. It's just going to be taking this little section. So I'm going to say I have one force applied here, right? As a resultant of this little segment that I have taken here. So this force is coming here as compressive force. I'm going to say it's coming this way. It's going to be coming also this way. And like this, right? And then like this, as compression. Say great. At the end, is going to be a force is going to be coming that way, right? Which is this compressive stresses. So if I give you these two forces here, I'm going to say if I have a component coming this way, another component is going to be completely horizontal. Let's give you the consequence. What's going to happen in the vertical direction? Shouldn't you expect another force coming that way to balance this force? You say this force is pushing this way, right? And then you have this force resisting. So what's going to happen? There is a small component of this force wants to go up, and this is going to be causing tension. So you should expect this tensile stresses throughout this dashed lines. So this dashed lines here is going to represent compressive stresses. Once the stress here become uniform as in compression in the x direction, you're good. You don't have any tensile stresses in the y direction. So this dashed line represents tensile stresses in the y direction. It's going to be like this. And on the bottom is going to be like this. Okay? So here's the problem. Once you put some compressive force here, it wants to open up this block. Now, how would you resist it? I mean, what is the easiest way of resisting this? You can say just add ties. So what I need to add is to add some ties in this direction here, right? This give you like a tie, and here's another tie, like rebars. This give you stirrups or ties, and this tie is going to be taking this tension force. But of course, you need to add some reinforce here in the top and the bottom to anchor the ties through it. It's going to be very similar to the shear design. We're going to provide here some ties to take this tension force. So this is kind of general idea so that you guys know what we're talking about here, what's the importance of having this end block analysis, right? And as I said, we have two types of end blocks or anchor zone. We have one for the pre-tension, we have another one for the post-tension. Let's go here through all of these notes just to understand what's going on. It says here concentration of compressive stresses occurs longitudinally at the supports of both pre-tension and post-tension. This is true, it happened in both cases. So whether you have pre-tension or post-tension, you're going to have here some tensile stresses and some highly compressive stresses. It's going to get transferred here from a local or a smaller area to a bigger area, which means the entire beam depth. For pre-tension beams, the stressing force gradually transfers to the surrounding concrete over a length of LT. You have your transfer length. Meaning, imagine here in a case like this, that this cable here is anchored or attached to, is bonded to the concrete. Now, transfer of this force, of this pre-stressing force, would need to have a certain length. And this length is called L sub T, transfer length. It is not necessarily equal to H or 2H, but we're going to see here a way to determine this length here. So over this distance here, all the forces can get transferred from the strain to the concrete. But in post-tension, there is no bond, in many cases, between the strands and between the concrete. And the force is going to be like a point load applied at the end of this end block, just outside of it. And this is a big difference between post-tension and pre-tension when it comes to end block design. So it says here for pre-tension, you're going to have the force transfer over L sub T. And in the post-tension, you don't have this gradual distribution. Why? Because the entire plate is just loaded from outside. So you don't have this transfer length. You have this transfer length when you have the pre-tension. But when you have the post-tension, this load is going to be applied from outside of the structure or the beam, and the stress distribution is going to take a shape like this, but it's going to be all concentrated out of the beam itself. This explanation of what happened, and let me show you this, here's what's going to happen. If you have here highly compressive stresses that you apply right here, right? Or you apply right here. You're going to have some tensile stresses develop in the Y direction. So you're going to have some tension coming this way and some tension coming this way. Once you go beyond the cracking stress, which is 7.5 square root of A prime C, let's give you like the limit cracking stress. This section here is going to start to open. We call this bursting crack. So what you need to do, you're going to provide some ties again, right? You're going to put some ties here in this direction here. You're going to put some ties. I'm going to show a picture of the ties and how it's going to look like and the direction of it. And this tie is going to bring or keep this concrete area here intact to prevent the cracks. So the problem, if you have any cracks here, that this anchor is going to start to move in, which means this box here, or this block, this anchor, if this is going to start to crack, it's going to start to move slightly in this direction. It's going to be a very small distance. Maybe you cannot see it with your eyes. But the problem of moving this block in this direction, it means that you're losing the pre-stressing. And this is going to be part of the loss that's going to happen to your pre-stressing force. So because once you start to move this block inside, it means the extension that you have provided here to the strand, you're going to be losing some of it. And you don't want this to happen. So this area of the beam needs to be really very rigid, and you cannot allow any movement of the end block or the bearing plate. You cannot allow this. Otherwise, you're going to be having more losses. I'm going to show you here a picture of the beam. So here's the beam. At this section here is going to be like an I section, and usually at the end is going to be like rectangular section. But in this beam detail, you see here that there is no rectangular section at the end. It just kept like that, right? This is the way it was designed. So these two lines are just straight. And look what happened. Usually, I would expect that this section here, this is where it's going to be the I section. And right here, most likely is going to be this rectangular section, which means this section right here. Look at the cable location. You're going to have high compressive stresses right here at this location. And you should expect some tensile stresses in the Y direction. This is why we're going to provide lots of ties. At the beginning, we're going to have more ties because it's expected the stresses here is going to be a little bit higher than anywhere else. And this location is also critical because if you are going to be having any relative movement, very small movement of this bearing block inside or bearing plate to the inside, it means that you're going to see here some losses in the pre-stressing. You don't want this to happen. And here is pi design. It's going to look like this. It's going to be like a vertical tie. And of course, you need to anchor it. So I'm expecting that I'm going to have here some rebars. You cannot just leave it this way, right? This picture is just showing here the pre-stressing strains. So another detail for a bridge, and it shows the strains, and it shows this ties. Look at the ties here. It's going to be like U-shaped ties and lots of reinforcement in the end of block. And you see the end of block? If you look here at the depth of this beam, you feel that this looks like kind of a square section, right? Isn't it? Like the length is almost equal to the depth, which is very common. This in the block, they usually take it from 1 to 2 times the beam total depth. So this length is roughly 1 to 2 times the beam depth to length. All right. Now let's look here what happened in pre-tension first. How about this transfer length? How to calculate it out? We have a length that we call development length, L sub D, which is composed of 2 sections or 2 lengths. The first one is called transfer length. This is where you transfer the force, initial force. And then after that, you have the flexure bond length. I'm going to explain the difference between the two. In this graph here, it shows the stress in the steel. Now, which is steel? I'm talking here about the strength, not the conventional rebar. And this is going to be the distance from the end block. So the beam is like this. Just keep this in mind, right? So first you have the compressive force, which is going to be right here at this location, right? It's going to be somewhere here. Now we need to transfer the force. Which force? It's going to be the effective force. Don't forget that you have the effective force, you have the initial force, right? FPI, and then you have FPE, and then FPS. FPS is the one that you need to use in your design when it comes to flexure strength, like capacity, the Feynman. And FPE is the effective one that you need to use when it comes to checks on the stresses within the beam. So first, you're going to have this length here, and look at the stress. If you imagine here that you have a cable, and let's say the cable is running this way, right? And then you have a plate right here, the anchorage plate is going to be right here. And in pre-tension, you don't really have any anchor plates, right? So in pre-tension, you're going to have direct connection between the cable and between the concrete itself. So I'm going to say here, I can remove this because it's not really needed in pre-tension. And I can make this short because what happened, they're going to trim the cable. They're going to be cutting it to be exactly this length. And from here to here is going to be some transfer of the force to P sub E. Now, at the beginning here, you don't have any stresses in the steel itself. If you cut the section right here, the stress is going to be equal to 0. The stress is going to increase gradually because now you are going to have anchorage between the rebar or between the strand and between the concrete. And it's going to start from the 0 point all the way to FPE. So look at the stress. This is going to be the stress distribution, right? So this value here is equal to FPE. I'm going to put it right here. This is going to be the level FPE. It's going to be right here at this point. Now, this section here, it is true that it's exposed to the compressive force. Coming from the strain. But when you look at the moment diagram, it's not really pushing it to the Feynman value. So M sub U here is going to be much less than Feynman. And here is going to be coming close to Feynman. And this point is going to be right at Feynman, which means this is the point that's going to be of maximum moment. So at this point here, the stress and the moment, this moment here is going to be at Feynman, which means this point. And the stress level in this location is going to be equal to FPS. So I'm going to say the stress here is going to be FPS. This is the one that you use in your design. This is why they call this going to be the transfer length. This is where you transfer the force FPE from the 0 point all the way to the FPE value. And from here to here is going to be the distance. This is going to be called flexure bond length. And this is going to be to take it from FPE all the way to FPS. This is why this length here, we have some empirical formulas for it. It says going to be 1/3 FPE times dB, the bar diameter. And here's going to be FPS, the difference between the stresses. FPS subtracting FPE times dB. This is going to be the flexure bond length. Total length is going to be called L sub D. So L sub D development length is going to be equal to the summation of this L sub T and LF. So we have this equation, empirical equation for the pretension, L sub T and L sub F, and here's L sub T. It says going to be FPE divided by 3 times dB. This is exact equation that I have right here. But in this case, divide by 1,000. Why? Because this is here in PSI. If you use this in PSI, you need to divide by 1,000 just to make it uniform. I mean, to the equation. This is empirical formula, so you cannot really justify it. You cannot say how much is the bond stress between the strain and between the concrete and try to drive it. You cannot do it this way, right? This is based on testing. So what you need to do is just use the equation as given. So I'm going to say here, LT is going to be equal to FPE in PSI times the bar diameter, the strain diameter, let's say 1/2 inch or 0.6 inches, divided by 3,000. For the flexure development length, is going to be equal to 1 divided by 1,000 to put it in KSI, and then it's going to be FPS minus FPE, which means the difference between the two levels. FPS minus FPE divided by 1,000 to put it in KSI, and then you multiply here by dB. It's going to be that simple. So you have a couple of equations here to figure out LT and LF, and just add them to figure out the full development length for the pretension beam. Here's the total length, L sub D. You just add the two to each other. So it's going to be FPS subtracting 2/3. Why subtracting 2/3? Now think about it. You just do the math, right? Now, how do we design here for the end zone? For the block, the end block. At the end, we're going to be using Caltrans method. Caltrans method is taken from AASHTO. Caltrans is the California Department of Transportation. They have their own design specifications for beams and girders, for all bridges, and they have a very simple method that you can use. So it says here that we have an empirical here equation to find out the stirrup force, which means the stresses and the forces in the y direction, the tensile stresses. And it says maybe about roughly 1% of what? Of PI, the initial pre-stress, divided by the height of the section, divided by L sub T. So where'd you get the L sub T from? I'm going to say you get it from here. Here's L sub T. So, okay. Just keep this in mind. It's going to be FPE 3,000 dB. So after you figure this out, L sub T, you come here to this equation, then figure out the amount of force expected in the y direction. This is going to be tension force. And then you say here, if you like to average the stresses within the stirrups and the ties, and also if you like to keep the stress in the tie to be kind of low, you don't want it to be at 60 KSI at the yield point. Because at the yield point, it means that you have enough strain in the tie. If you have enough strain in the tie, it means the tie is going to start to open up. If the tie is opening it up, so what's going to happen? Some slippage is going to happen for the strain itself. And if you have any slippage in the strain, it means that you have losses. You have more losses in the pre-stressing force. You don't want this to happen. So we're going to control it here and keep it up to 20,000 psi instead of 60,000 psi in the tie itself. We have here quick numerical example. It's so simple. They give you your PI, which you guys know how to figure it out. You decide the number of strands, and then you have FPI for each strand, and then you have the cross-section area for it. And you simply figure out L sub T. Based on this given information, you can figure out L sub T. So you take FPE divided by 3,000 times 1/2 inch. So you have about, let's say, 26 inches. Say, okay, 26 inches. How about the cross-section area for the steel that I need? We're going to say first you need to have the force. So let's see first how much force you expect to have there. if you look here at this equation here, this combination of the two equations that we have looked at, here's the two equations. Here's one equation, F is going to be equal to 1% of PI times H divided by L sub T. And if you want to find out this AT, you're going to say AT is going to be equal to the force, which is this equation here, times 2 divided by Fs, which means this equation. So this equation here is going to give you here the total amount of cross-section area of the ties or the stirrups based on PI, the height, Fs, the 20 KSI, and the length of transfer. This is exactly what we have used here in this equation. We have used the previous equation I just showed you. Based on this equation here, you need 0.6 square inches roughly for cross-section area of the ties. If you try here to use, let's say here's a beam, and then you decide here to use number 3. When you cut through number 3, the force, right? If you cut through number 3, it means that you're going to have 2 times 0.11 square inches for each one of this stirrup leg. You're going to have 0.22 square inches. Now you need 0.61, which means that you need 3 ties. So we're going to provide here 3 ties next to each other, and this should be able to resist the tension force. You say, okay, this is just a quick example to explain how it is done conceptually. But let's see what Caltron's design specifications would say on this. Here's Caltron's design specifications. And this is kind of recent, this 2018, as you see here. And it says here, we're not going to be doing any of that. Just going to give you here a simple approach. And they just say the amount of tension force, vertical tension force in the y direction, right? They're going to say it is going to be equal to roughly, I'm going to show you this here for quick, 4% of the pre-stressing force. I have here a quick question that came through from Teresa. She's asking about the total length and units. So as I said, that this empirical formula here, so you cannot really justify it like this, for example. How would you justify this? It's just empirical formula. So you cannot really do your units with it. And also, as it says here, if you want to use it in this equation here, it needs to be in PSI. So it is just like that. It's an empirical formula, which means based on testing. So they do some testing, and then they do comparison here, or relationship between FPE and FPI and dB and the length, and then after that they come up with this equation. This is why they call it empirical formula. So there is no basis for it. You cannot really figure out a rational way of determining the length based on this FPE and dB, and there is not. So let me show you here what happened in Caltron design specifications. They said this PR, you're going to be taking it as 4% of PI. So, okay, just look at the axial force. Don't worry about the transfer length. Just take the transfer force here, PI, take 4% of it and consider it to be acting vertically, which means this is going to be the tension force. This PR is going to be the tension force. Tension force in the y direction is going to be equal to 4% of the axial force. You say, okay, good. So what do you do after that? They just say, design the ties to take this, but be sure that the stresses within the tie is not going to be going beyond 20 KSI. So, okay, it's much easier. Now, let me go back here to my example and see how would I relate this to the Caltron design specifications. Let me take here this 376 KSI, 376, excuse me, kips. Take 4% of this. What does it mean by that? Can someone help me with this? 4% of this force, how much?
This is 15044.4.
So 15 kips? Okay.
Yeah.
15.44, good, all right. Take this, 15 kips, divided by 20 KSI. To figure out the amount of reinforcing needed, right?
0.752.
0.752. You see what you get here based on that? So what happened, Caltrans is providing here kind of more, I'm gonna say, conservative equation. They just say take 4% of this axial force. So whatever axial force that you have, just multiply by 0.04. And with that, you're gonna have this force PR. So this PR is gonna be equal to 4%. So let me write it down here. I'm gonna say 0.04 PI, this is gonna be the force, equals AS times 20 KSI. Make sense? So what's the 20 KSI? It's gonna be FS. And this is gonna be AS for the tie itself. And what is PR? It's gonna be 4% of PR. So I don't need here a transfer length. I don't need anything. So the equation is gonna be so simple. For pre-tension, all what you need to do is to take 4% of the axial compressive force, the pre-stressing force, and just provide reinforcement to take this tension force. It's gonna be much easier. Any questions? Yes? No questions? All right, let's see an example based on Caltrans. They say that we have 16.6 inch. So the diameter is going to be 0.6 inch. Grade 270 strength. The cross-section area for each one of this 0.6 is going to be 0.217 square inches. You have 16 of these, therefore you have 3.42 square inches. So this is going to be the total, right? Cross-section area of the strength. That's great. Let's say that PI is going to be at roughly 0.75 times 270 KSI. What is the magic number that you use instead of 0.75 times 270? Can someone remind me, please?
4%.
No. What number do we use instead of 0.75 times 270? What is FPI that we usually used to use?
0.4.
No, I'm asking about FPI. What the FPI value that we usually use?
150.
189?
Yeah, 189.
189 KSI. How about in this example here? What did they use? They use 75% of 270. How much is this? I need your help.
202.5.
Okay. KSI. This is higher than 189, but this is okay in bridges, right? You see, there is lots of design values that you can use in your analysis. And you should be fine. This is acceptable because you use higher value than the 189. If you remember in the past, I used one example. We usually use 150 for FPE. Am I correct? For FPE, what do we use for FPE? 150 KSI. You remember this example at which we used 155? Do you guys recall this example?
Yeah.
Okay, so it depends. So what I'm trying to say is there is no just one set value. It depends on the design methodology, it depends on the company, and depends on the type of mechanism and reducing the losses. So here they're expecting that they're going to be able to take it all the way to 75% of the 270. So I don't want someone here to come and say, but we usually use 189. Should I change it? I can say no. In this example, it is clear that they'd like to use 202 KSI for the FPI. So I'm okay with this. When you take this FPI multiplied by APS, it's going to give you here PI, turn to be 700 kips roughly. So I'm going to say about 700 kips. According to Caltrans design specifications, I'm going to be taking 4% of this number. So now we're going to be taking 4% of the 703 kips. Now let's see what's gonna happen. Here is 4% of the 703 kips. You're gonna end up with 28 kips or 28.1 kips for the PR. So what does mean by PR? If this is gonna be your beam, and this is gonna be like the end block, this is gonna be the force, this is gonna be pulling this stirrups up. So we're gonna say this is gonna be FPR. So we're gonna write it next to it. PR is gonna be this force here, 28.1 kips. Now you would like to keep the stresses within the steel here to be 20 KSI max. I understand that if you take AS multiplied by the stress, it's going to give you here the force. So therefore, AS is going to be equal to 28.1 kips divided by 20 KSI, end up with 1.41 square inches needed for all the stirrups. Not just for one stirrup, this is going to be for all the stirrups. Now, how would I put the stirrups? I'm going to put here's the beam again. The stirrups is going to be like this. It's going to be a few of them, not just one. Right? A few stirrups. At each one of them, you're going to be cutting 2 legs of the stirrup. So if you say here, if I'm planning here to use number 5 bars with 2 vertical legs, because it's going to be a stirrup or a tie, it means for each stirrup or each tie, I'm going to have a total of 0.62 square inches. So what is 0.31? 0.31 is going to be AB for number 5 times 2. Why times 2? Because I have 2 legs. Here's the total square inches needed for this end zone. So I'm going to take the 1.41 divided by the 0.62 for each tie. You end up with 2.3, meaning I need 2.3 ties. So go ahead and provide, let's say, 4 or provide 3 at least. So you need here to have at least 3 ties. But most likely you're going to put maybe 5 or 6 in this location, right? Because think about the spacing here. What spacing would you like to put this ties at? And how much is the cost of putting, let's say, number 5 as a tie? You're going to see it's going to be very small. I'll place it maybe at 4 inches and maybe a few of them is going to be okay, as long as you cover the 3 ties needed. So all what I need here is only 3 ties, but I'm going to provide more, certainly. Here's this section. This is the way it's going to look like. This is going to be the stirrup, and as you see here, it's going to be hooked at the bottom, and of course I'm going to have here some rebars so that this is going to be hooked around them, right? And then the top, this is going to be the concrete deck. You're going to have reinforcement of the concrete deck, and of course you're going to have your couple of bars of the concrete deck is going to be running this way. Because if you don't have an anchorage of this rebar in the top and the bottom, it means this rebar can easily slip. So you need to have an anchorage top and bottom for the rebar. So when you apply any tension to it, it's going to see here some resistance. Any questions? On this design methodology? So simple.
Where
Yes, go ahead, please.
where do the number 5 rebars come? Oh, that just previously given, right?
Here, we said that we're going to be using here number 5 bars, right?
Oh, it says 4 on the drawing. I don't know. That's different.
We're here.
The 4 number 5
This gave me this
continuous.
He's pointing at this bar. 1, 2, 3, 4.
Okay.
With number
thank
5, continuous reinforcement. This is different issue. I'm talking about
Okay.
here the vertical rebars, the stirrups, like in here, in this section. If you'd like to consider this to be the beam section, right? These few lines that I've just drawn here, right? This give you the 3 ties that we're talking about. And as it says here, therefore use 3 number 5, double legs within h/4. So you're gonna put it here. You see the spacing? It's gonna be very small. You're gonna put the 3 within 10.5 inch, which means the space is gonna be about 5 inch between each tie and the other. In reality, I'd add maybe 5 to 6 and I'm gonna put them at 4-inch space. Okay.
Okay, thank you.
All right, thank you. Any other questions on this design methodology? So simple. You take 4% of the compressive force, the pre-stressing force, and put some ties to take this force based on 20 KSI max. That's it. All right. With that, I'm done for today. I'm gonna go right now to the office Zoom meeting. I'm gonna be waiting for you. Again, I'm gonna bring here one by one. So please don't feel it's taking too much time if I didn't get back to you right away.